This is the first section in section 6.1 on slope fields. And if we take a look at this aerial view here, we see a lot of farmers' fields. And so you notice that each piece of this farmer's field kind of has different information about it. We've got stuff that is being farmed that looks like it's pretty nice and green. We have stuff that's brown, which maybe is not being farmed. We've got stuff that's kind of yellow, which might look like something that was just planted. So it's got a lot of information stored in it. And just like farmers' fields, slope fields also have lots of information within their field as well. And so you might see a general shape here that looks maybe circular or maybe like an oval. And each one of these short lines tells a different story about what's happening in this region on the coordinate plane. So we're going to take a look at these slope fields, and we're going to see how these slope fields help us to understand anti-differentiation. So, and remember, anti-differentiation is reversing the differentiation process. And so let's just do a little review first. For instance, let's consider the function y equals x squared plus 3. If we take the derivative of that, we get 2x. Let's take a separate function, y equals x squared minus 5. You might notice some similarities, you might notice some differences from the first function. This derivative is also 2x. So here we have two different functions that have the same derivative. And so if we then look at what happened to the 3 or the negative 5, we know that those derivatives of constants are 0. And so they disappear. So if we try to reverse the operation, in other words, start with 2x and get back to a function, in other words, find the antiderivative, then what happens is we know we need to reverse the derivative rule. So we have to find that function that when differentiated give us 2x. So in other words, we got to bump up the power and divide by the new power. So we know that that ends up being x squared. But the real question is, what is this function, after we go through this anti-differentiation process, is this function x squared plus 3 or x squared minus 5? Or is it x squared plus or minus something else? So the process of anti-differentiation includes a plus c on the end of what was been anti-differentiated. So we found the antiderivative of 2x, it's x squared, it's that big F, that parent function, so to speak, that when differentiated gives us 2x. And the plus c then represents any possibility, like a plus 3 or a minus 5. It just represents any possibility that could be out here that would lead to the same derivative. And so since we don't really know specifically what number to put in, we just put in a c. And right now we just lack the information to find that specific number. So if you're following along with paper notes, the graph that we're about to display here is just for discussion purposes only. You don't need to graph this on your notes. I'll tell you when to graph on that grid in your notes. But we're going to talk about the indefinite integral here. And so we talk about an indefinite integral as the set of all antiderivatives of a function. So if we remember back to our conversations of big F and little f and antiderivatives, and this goes all the way back to chapter 4. Little f is a derivative, and when we find big F, that function whose derivative is little f, we then say that when we take the antiderivative of little f, that's what this whole left side means, that equals that big F, that parent function, plus c. So that c creates this phrase here, the set of all antiderivatives. In other words, that c could be 3 or minus 5 or something else. So we know the little f is the derivative. That's our lingo back from chapter 4. We know big F is the antiderivative, and really I was kind of glossing over that in chapter 4. Big F, I should have a capital F here. really is, the antiderivative is really big F plus C. It's that whole thing in the box. Because the antiderivative is really that family of functions, or that's, in math terms, the set of all antiderivatives, a set being a collection of more than one thing or several things. So this is a collection of functions that all might have different C's, might have a +3, might have a -5, might be something else. So it represents, so this antiderivative, when we have this plus C on the end, which represents that family of functions. So when we talk about this graphically then, and we go back to our example that we started with, the derivative of y prime equal 2x, then we know we got that derivative 2x from these two functions. So if you notice, if you think derivative, and when I ask you things like I say derivative, you think slope, or vice versa. If we know the slope is the contour of the curve, so we can see that these contours are very similar at the same location of x, which is why they have the same derivative. So if we include the whole family here, this blue curve and this red curve are the ones we started with, but if we include all the members of the family of curves of x squared plus c, all that means is that we have a different c, and that represents a different curve. So a c of 3 gets us our blue curve, a c of -5, constant of -5 gets us this red curve, a constant of -4 gets us this green curve, a constant of -3 gets us this brown curve, and so on and so forth. But no matter what that c value is, when we take the derivative, we get 2x. And so if we graph derivative values, and that's what showed up here when I clicked, if we graph the derivative values for every location of x, if you notice the derivative values we show by these short lines. And so, for instance, along the y-axis here, where x is equal to 0, if we plug in 0 here, 2 times 0 is 0. And so what that is saying is that for this entire family, no matter what specific function I pick, they're all going to have a tangent line or a slope of 0 right at, when x is equal to 0, right along this y-axis. Their tangent lines are all horizontal. And if you notice there, if we go out to 1 here, and plug in 1 to the derivative expression, 2 times 1 is 2. And so when x is equal to 1, we see all of these slopes here, these short black lines. We see all these slopes that have a slope of 2. And so we know the slope of the tangent line for any one of these functions. It doesn't matter if I'm talking about the purple one or the orange one or the blue one. When x is equal to 1, those slopes are all 2. So they all have that same contour. Everyone in the family does. And that's because they all follow the same slope field. So these black short lines are the slope values, the numeric values we get when we plug in different values of x into the derivative equation. So today, really, we're going to focus on drawing these, finding those values and drawing these. And so, and then we're also going to focus on finding a specific function among the family. So, and when we do that, when we find that specific function, that's called an initial value problem. And so, first of all, we're going to represent our derivative expression with a slope field. And so slope fields, we call them a learning tool. They're usually computer generated, but we really expect students to draw some smaller ones by hand. So nothing to the extent as what you see here, but maybe graphing a dozen or maybe 18 points. So when I say slope, you think derivative. We've gone through that several times. So when I talk about a slope field, which are these little black lines, then really what we're saying is we're looking at a field of derivative values. So again, we know this derivative is 2x, and if we stick an x value of 0 in, then we get a derivative value of 0, which is a horizontal line. So notice all of these horizontal lines are my derivative values. So our definition then of a slope field, and this is in your notes, is this. So sometimes we call it a direction field, but the slope field is the derivative. And so I'm using the Leibniz notation here, dy dx, or I could use y prime. So a slope field is a derivative expression, and the derivative expression can be a function itself. So if we think of this slope field being y prime equals 2x, that in itself is a function. 2x is a function. So it's a function, and that function can be written in terms of x or y. So we might see a variable x, we might see a variable y in the expression, and that just means we're plugging in x and y values on our grid. So and the way we make a slope field is we have a plot of short line segments. So notice these black segments are nice and short, with slopes. And their slope values are whatever number we get when we plug in the coordinates for x and y. And we do that for what we call lattice points, or points on the graph. Lattice points are where the grid lines intersect. So we're finally using that big graph on your piece of paper now, okay? So we have this graph here, and we're going to go back to that original expression. We want to graph the slope field for the derivative y prime equals 2x. That's like dy dx equals 2x. And so we have to look at this. We know that when we plug in values here to get a number, but we're looking at derivative values. Okay, that's all a slope field is. So our derivative is 2x. So we think, okay, we look at this and we say, well, if I put an x of 0 in, and I do my math, 2 times 0 is 0. That means when x is equal to 0, which is all along here, okay, then I'm going to have derivatives equal to 0. So my slope lines are going to look like that. Okay, this short line segments with slope of 0. Let's plug in a different value for x. Now let's plug in an x value of 1. So 2 times 1 is 2. So where x is equal to 1, which is all along this line, we're going to have a slope field with slopes of value 2. Now there are some values that we really expect you to be able to draw accurately on a grid. A slope of 0, we should be able to see you draw a definite horizontal line. A slope of 1, 1 means over 1 and up 1. So a slope of 1 would look like something that would travel along the diagonal between the boxes. So this being a slope of 2, the way graders would grade a slope of 2 is they would eyeball a slope of 1, and they would make sure that your slope of 2 was steeper. So here's the slope of 2, and if you notice, that's steeper than drawing the diagonal. So that would be acceptable for a slope of 2. So then we go ahead and plug in a value of 2 for x. So 2 times 2 is 4. And then let's kind of talk about the grading again. So when x is equal to 2, we have to draw something with a slope of 4. Now, it's almost impossible to tell if it's drawn exactly at a 4-to-1 ratio. But what we look for is that when we are at an x value of 2, we have lines that are steeper than the lines before. So this is kind of how we grade. We grade flat, steep, and steeper. And as long as we see flat, steep, and steeper, then you're going to get credit for these slope values. And then we want to talk about, we can talk about putting 3 in here and getting a slope of 6. And so we would grade that as steeper yet. So we just look for those general patterns. And then we look for things that you can use to make this go quicker. For instance, if we stick -1 in here, and -2 in here, and -3 in here, okay, then we get -2, -4, -6. So we know that we have a mirror image over on this side of the grid. So there are the slope, there's the slope field for 2x. And so we can kind of see that if we started here, these slope fields kind of are directional. If we start here and we follow our slope line down, it's pointing towards here. And so as we get closer to here, we see that our slope is a little flatter, so we go a little flatter. And then as we get to here, we see our slope is really flat, so we know we have a minimum. And then this is going to push us in this direction, and we're going to come over here, and we just see that we got to start going up because that's what this line is telling us. And then we're going to get over here, and we're going to go up even faster because that's what this line is telling us, and so forth. So we can get a good sketch at this point. So if you notice the comparison between what we calculated and what I had there earlier, those are really close. Just that what I had there earlier was a lot more values calculated, more than you would ever be expected to calculate. Even what we did is more than typical. So, so now to take the value of the derivative and solve an initial value problems, it goes like this. Initial value problems are finding the value for c. So for instance, if we have that derivative, y prime is 2x, we call that a differential equation. And it's a fancy term, but basically means the equation for a derivative. And so we have y prime equals 2x, and it goes through the point 1, 4. So we know that we're going to have to take this differential equation, and we're going to have to find the antiderivative. We're going to have to do antidifferentiation. So we're going to go ahead and set up the differential equation. We're going to rewrite it in Leibniz notation, and then we're going to do something fancy. It's called separating the variables. All it means is we're going to take the dx and put it over here on the x side. Okay, and that way all my x's are on one side, all my y's are on the other. And then we're going to anti-differentiate both sides. Now you might look at this and say, well, this is identical. I'm going to click the mouse again, and you're going to see our anti-differentiation symbols, or our integration symbols, show up. So that's what it means to anti-differentiate both sides. It means that you're putting that symbol out in front. And so now we're going to have to do the antiderivative. So on the left-hand side, you can think of this as 1 dy. So the antiderivative of 1 is just y. And then the antiderivative of 2x is x squared, right? It's 2 times x squared over 2. And then since we did the antiderivative, we put that plus c. So in other words, we know we have a family of x squared functions, and we know we have a constant out here that we need to find. And the way we find this constant is we use this information. When x is 1, y is 4. So we're going to put a 1 here and a 4 there. And so when we have this expression with our plus c, we just call that a general solution. After we start plugging in that initial condition or initial value, then we start to get to a very specific solution. So solving that for c, we get a c equal to 3. We're going to put that 3 right back up into here. And so we have a function y equals x squared plus 3. That function is going to go through 1, 4, and it's going to follow this slope field y prime equals 2x. So we call that a particular solution. When we've replaced the plus c with a specific number. So just to kind of recap, solving an initial value problems, it involves anti-differentiation, so setting up the expression to take the antiderivative, finding c and plugging that value back into the function. So going back to that big graph paper, or that big graph on your paper again, we're going to graph the particular solution x squared plus 3. So here's that particular solution, right? It's an x squared and it's moved up 3. And if you notice, here's 1, 4. It goes through that point 1, 4. Okay? So that's that initial condition. The nice thing is that we can actually sketch that solution without all of the problem solving. And we're going to try doing this on the next 2 examples. So we're going to intentionally not do the initial value portion. We're just going to get the slope field, and we're going to sketch the curve. So we're going to show you how to do that even though we're not doing all the calculus involved. So for instance, here's a differential equation. It's y prime equals negative 3x. So we're going to sketch that on this field, this part of the coordinate plane. So if you notice, we have minus 3x. There's no y in here. We'll introduce the y variable a little bit later. So really what that is saying is it doesn't matter what y is. It's not going to change the value of the derivative. So kind of like the other one, let's go ahead and start off with x equals 0. So negative 3 times 0 is 0. And even if we let y equal 1 and x is still 0, so now we're looking at this point, we're still going to get a derivative value of 0. Even if we let y equal 2, looking at this point, we're still going to get a derivative value of 0. So as you can see, because y never shows up in the expression for the derivative, or the expression for the differential equation, since there's no y in that expression, it doesn't matter what y is, the derivative will always be the same value. So it doesn't matter, it's just that we know whenever x is 0, the derivative is 0. So let's change our x value. Let's look at an x value of 1. So when we put 1 in here, 1 times negative 3 is negative 3. And it doesn't matter if we look at this value, 1 comma 1, derivative is still going to be negative 3. Okay, so we know that we're going to have a derivative of negative 3 all along this location. So what that really means, as I'm graphing it, you notice that, first of all, we know 1 will be the diagonal. So we're looking for something steeper because it's negative 3. So we're looking for something steeper and negative. And that's all we're grading for. Let's change up our x value to 2. So we put 2 in here. 2 times negative 3 is negative 6. So I know these are all negative 6. So as I'm grading this, I'm looking for 0 slope. I'm looking for horizontal, steep and steeper. Now we can come over here to these points. And when x is equal to negative 1, negative 1 times negative 3 is positive 3. So I should have slopes of positive 3 here. So when I'm grading this, I'm looking for the same steepness as this, but positive. And then when x is negative 2 times negative 3 is negative 6, or is positive 6, excuse me. So I'm looking for steeper yet, and I'm looking for the same steepness, but positive. So that's how I'm grading this, being an AP grader. Now I want to, so here's my slope field, and I want to sketch the function through 0, 2. So here's 0, 2. And the nice thing is I can do this without solving the initial value problem. We're not going to solve the initial value problem at all. So I'm going to graph point 0, 2. So there it is in green. And I'm going to follow my slope lines. So basically this slope line here, this red line, is telling me to start out from this point and go horizontally in both directions. And then that's going to move me towards these values of slopes. And these values of slopes are telling me to turn vertical. And then as I surpass these values for slope are saying to keep that vertical trend but get steeper. So what I do is I make a smooth curve and I follow the slope fields, and I start at the point and move in one direction. Okay, so I'm going to start and make the left-hand side of that curve. And then I'm going to come back to the point and make the right-hand side of that curve. So my function looks something like that. And it might not cross exactly where it's supposed to, and that's okay. We're just getting a general shape here. If we don't solve it for the specific function, we can't get any more exact than this. So, so just to kind of back up, when we're sketching this, we start at that initial value point, and we graph one way from that point, and then come back to the point and graph the other way. On your TI, on your graphing calculator, you should have a slope field program, and that slope field program you can enter the differential equation dy dx, so you can enter minus 3x. You can enter the known solution if you want to, and we didn't solve for this, but I'll tell you right now that known solution is minus 3x, 3 halves x squared plus 2. But we didn't solve for it, but you can enter that specific solution if you'd like to. And then you can view the slope field. And so when you view the slope field, this is what you'll view. Is a picture pretty similar to what we just drew on the previous screen. Now let's take a look at a differential equation where there is an x and a y. So now we know that both of these columns values are contributing to this product, contributing to the value of the slope. There are still things we can do to make the sketching though, or to make the sketching of the slope curve, the slope field go faster. And that is, let's first start working with things that make this 0. So for instance, when x equals 0, then this whole thing is 0. So when x is 0 and y is 0, the derivative is 0. When x is 0 and y is 1, the derivative is still 0. When x is 0 and y is 2, the derivative is still 0. So if you notice, all up and down where x is 0, we have a slope of 0. And we can also do likewise with y. When y is 0 and x is 1, which is right here, we also have a slope of 0. When x is 2 and y is 0, we also have a slope of 0. So we also know that, and we can go on to say the same thing about out here at 3. So we know that along this axis we have 0 derivative values as well. So now we've got these 16 points to look at. And so now what I start to do is I get kind of a little critical, and I say, okay, let's look at these 4 points. Because these 4 points are either 1, 1, minus 1, 1, minus 1, minus 1, right? Or 1, minus 1. So they're all 1s, but they're either pluses or minuses. So I kind of put that in the table like this. Could be a +1, could be a -1. The fact is we're going to come up to this differential equation, put a 1 here and put a 1 here. And if we multiply 1 times 1, we're going to get 1. Or we're going to get -1 if one of them is negative. So we know then these 4 points are going to have a slope of 1. And it's either going to be positive or negative depending upon the coordinate. So likewise, we can look at the 2's. So here and here and here and here. If we put a 2 and a 2, the product is going to be 4, and it's going to be either positive or negative, depending upon what coordinate we're in. And then what if we start mixing them up? What if we start letting one be a 1 and the other be a 2? Well, if we multiply those together, we're going to get 2. And again, depending upon where we are, it's going to be either positive or negative. And then what if we flip that, let the first one be 2 and the second one be 1? Multiplying those together, again, we're going to get a 2. And positive or negative depending upon where we are. So if we look at the first quadrant where they're all positive, we're going to have a +1, which is going to go right along the diagonal. Then we're going to have a +4, which is going to be really steep. And then these two are going to be +2, which is going to be not so steep. So it looks like that. So here's a slope of 1, here's a slope of 2, which is steeper, and here's a slope of 4. When x is positive, all of these slopes become, when x is negative, all of these slopes become negative. When they're both negative, all of the slopes become positive again. So as a grader, what I'm looking for is I'm looking for 1 and 1 and -1 and -1. Okay, and then I'm looking for positive but steeper, positive but steeper, negative but steeper, negative but steeper. And then I'm looking at positive and steepest, positive and steepest, negative and steepest, negative and steepest. So that's kind of how we're grading that. So that's what this differential equation, this slope field looks like. Okay, and now we're going to sketch a possible solution through 2, 1. So here's 2, 1 right here. And like I said a little earlier, we can graph the slope, we can graph a slope field, and we can graph a solution without doing any math, which is the nice thing. So we're going to graph point 2, 1, and this is kind of like what they do as a meteorologist on the weather when they show you the high and low pressures centers. That those are nothing more than slope fields. And so now what we can do then to sketch the solution here through 2, 1 first thing we're going to do is graph the point at 2, 1. So we're going to go over 2, up 1, and we're going to graph that point. So there it is in green. And then to sketch the solution, we want to use the slope field as a directional guide. So for instance, here we are at the point. If we move this way from the point, the slope field is telling us to move up and to the right. And if we move this way from the point, the slope field, if we follow the field line, it's telling us to move down and left. And then as we come to here, since it's telling us to move down and left, it's kind of telling us to use this information. And so as we go down and left, then we need to be flat. Okay. And so we need to be kind of between flat and positive. And then as we get closer to this location, we need to be even flatter. And then once we get past this location, if we look at this information here, it says start to bend upward. And so, and then it says as we go past here and we come to this location, it says it's telling us to get steeper and continue to bend upward. So if we notice then, when we have slope lines here that line up with an axis that are drawn right on the axis, not across, but right on the axis, this is actually an asymptote. So as we graph this, then we're going to make this smooth curve. We're going to start at the point and move one direction, and then we're going to come back to the point and move the other direction. So there's that horizontal asymptote I was talking about. And so we're going to follow, see how we follow that slope line with the green curve? We're kind of right along that slope line and getting steeper. And then we're going to do the same thing in this direction. We're going to go right along, that slope line, get flatter yet, and then come back up again. And so this might look a little pointy in these two regions, and that's okay. It's not the best drawing, but that's about what it looks like. And again, we don't even know what this equation is, this function is, and that's okay. It just has some basic shape like this. I'm pretty sure it's not a parabola though, because parabolas are just in a function of x. At least parabolas that would look like that. So it's something, but it's not something we're going to concern ourselves with finding until the end of this chapter. We can also do this on our calculator slope field. So when we input the differential equation, we're going to have to input an x and a y. And that's a typo. It should say x times y. And you do that using your alpha key. So you'll use to get your x, you'll use your x key, your variable key. And then to get the y, you'll do an alpha. Alpha is right underneath the second key, so you'll do an alpha, and then y is number 1. So it's going to be doing an alpha 1. That's what this means right here. And then you get x, y. And then this known solution, I know how to solve this, and you will too by the end of the chapter. This known solution is actually this, 1 over e squared times e to the power x squared over 2. And don't concern yourself with knowing how to do this yet. That's way for the end of the chapter. But if you want to put that in to number 2, the known solution, you can. I didn't down here. I just went ahead and graphed the slope field. But if you want to enter the differential equation, you can. Sometimes, though, we need to solve the initial value problem. Sometimes we just need to do the calculus. And sometimes we just don't even bother doing the slope field. So we're going to try that on a couple of examples. So for instance, here's a differential equation. It's dy dx equals sine x. And so we're going to just develop a methodology here of solving these initial value problems and coming up with that what we call that particular solution. So we're going to, this isn't much of a rewrite. It looks exactly like what it is above. But we're going to separate our variables. So we're going to put dx into the right side here. And then we're going to go ahead and anti-differentiate. The antiderivative of dy is y. And the antiderivative of sine x is, we have to think of that function when differentiated gets a sine. So that's minus cosine x and then plus c. And then this initial condition is what we're going to use to figure out what our c is. So this is function notation. Y of pi is the same as saying like f of x. So when the function y, when the x value is pi, the y value is 3. So that just means we put pi here, and we put 3 here, and we have 3 equals minus cosine pi plus c. Now if you think about the unit circle, here's our unit circle. I'm just kind of drawing it in space here. Okay, and pi is over here on the left-hand side. Remember, cosine is the x-coordinate, and that x-coordinate is -1. So cosine of pi is -1, so we have the opposite of a -1, and that's a +1. And so now we can solve for c. So subtracting 1 from both sides gives us a c of 2, which means the particular solution then is minus cosine x plus 2. So there's our particular solution for this differential equation. Here's another example. Let's take the differential equation. Now this is the second derivative, so this is kind of an interesting one. We're going to have to go through this twice. Okay, so we have a second derivative. It's 2 minus 12x, and we have two initial conditions. When x is 0, the derivative is 4. The first derivative is 4. And when x is 0, the function itself is -3. So we have to go from the second derivative to the first derivative to the function. It's kind of a multi-tiered process. But the steps don't change. We have a differential equation. We're going to temporarily call this first derivative instead of the second derivative. So I'm just going to call it dz dt. I just picked another variable I wasn't using. And so now now that I have a first derivative expression here, I can separate my variables and do an antiderivative and get z equals, okay? And then doing the antiderivative here, this is 2x minus, and then 12 times x squared over 2. Right, bump up the power, divide by the new power, plus c. So when I simplify this, that's z equals 2x minus 6x squared plus c. So this z is really y prime, right? I just said temporarily call this the first derivative. So so really what we're saying is use this initial condition, because if I take the antiderivative of this, I've then go from the second derivative to the first derivative. So so this general solution, then we're going to use this initial condition. So when x is 0, y is 4. So I'm going to put zeros here and a 4 here. And when we do that, x is 0, z is 4. So when we put our 4 here and our zeros here, we get a c value of 4. So the particular solution here in terms of z is 2x minus 6x squared plus 4. Okay, but that really is dy dx, right? We've done the antiderivative process, or we've integrated, so to speak, once. So we've gone from the second derivative to the first derivative. So so really, this equation is really dy dx. It's really the first derivative. And so now we're going to have to go through this whole process again to get the function. So we're going to separate our variables. We're going to take the antiderivative of both sides. This side being just the antiderivative of dy is going to be y. And then doing the antiderivative here, we're going to get 2 times x squared over 2 minus 6 times x squared over 3 plus 4x plus c. And now we can plug in this information. When x is 0, y is -3. So, oh yeah, let's simplify this a little bit. There we go. And then we'll go ahead and plug in when x is 0, y is -3. So -3, 0 squared minus 2 times 0 cubed plus 4 times 0 plus c. So c is -3. And so now I can put that back into here and get the particular solution for the function itself. So I got x squared minus 2x cubed plus 4x minus 3. So there's that particular solution. So how can slope fields help us understand antidifferentiation? We know that slope fields represent a place where families of function can be sketched. So we know that we have, just going back to all of those parabolas that were sketched at the beginning, of the discussion, we can sketch whole entire families of functions. And then when we solve that initial condition problem, we're finding that single function that we want to go through a specific point. So at this point, you can do your day one antiderivatives homework. It's a 2-day. This is a 2-day section. So after the second day, if you feel like it, you could do a proficiency exam in Blackboard instead.